There is something out there, something older than the oldest star, heavier than the heaviest black hole, yet perfectly, defiantly silent. It does not glow. It will never warm your skin, nor shimmer in any telescope. And still, without it, every galaxy would unwind, every planet would drift away, every cradle for life would be torn apart. We cannot see it, cannot touch it, but it cradles the cosmos like an unseen hand. Astronomers call it dark matter. Tonight, we follow its shadow among the stars. In 1933, perched high atop Mount Wilson, Swiss-American astronomer Fritz Zwicky turned the massive 100-inch Hooker telescope toward a distant swarm of galaxies, what we now call the Coma Cluster. 1,000 galaxies gliding in a slow, silent ballet across the dark. He measured their motion, traced their paths, and then blinked in disbelief. They weren't drifting gently, as expected. They were tearing through space like hornets in a sealed jar, chaotic, furious, too fast to be bound by the visible matter around them. By every law of Newton and Einstein, the cluster should fly apart, but it didn't. Zwicky did the math, counted the stars, the gas, the light, and found it lacking. To hold these galaxies in place, something unseen must be at work. An invisible force, a hidden mass. Dunkel Matari, he whispered. Dark matter. Not a poetic turn of phrase, a necessary explanation. He estimated that this unseen material outweighed everything visible by a factor of 9. 9 parts mystery to every 1 part light. His colleagues raised eyebrows, shrugged, dismissed him as a crank. A man with wild ideas, untethered from convention. But Zwicky had glimpsed something true, something vast. And in that moment, the cosmos had whispered its first secret. A truth hiding not in what we could see, but in what we couldn't. Nearly 4 decades after Zwicky's revelation slipped into obscurity, a quiet revolution began under the desert skies of Arizona. At the Kitt Peak National Observatory, Vera Rubin and her collaborator Kent Ford turned their spectrograph toward Andromeda, our neighboring galaxy, spinning in silence across the void. They weren't hunting stars, or listening for motion. According to Newton, stars near the galactic center should spin fast, pulled tight by gravity, while those on the outer edge should lag behind, like children clinging to the rim of a spinning carousel. But that's not what they found. As Rubin traced the swirl of starlight, she saw something impossible. The stars on the edge weren't slowing. They were racing, locked into a flat, unwavering velocity curve, a plateau that defied expectation. There was no drop, no tapering, only speed. Something unseen was at work, something massive, clamping the galaxy in its grasp, extending far beyond what any telescope could see. Rubin understood what she was witnessing. An invisible halo of matter, a gravitational scaffolding surrounding Andromeda and likely every galaxy in the sky. She smiled at the elegance of it, not with triumph, but with quiet reverence. The universe, she said, is not made of what we think it is made of. Again and again, the numbers fell short. The equations were elegant, relentless, but tallied less than the sky required. It was as if creation itself were playing hide-and-seek with mass. Take everything that glows and flickers, every star, every nebula, every planet, every last photon of starlight. Gather them into a scale. Weigh the glittering cosmos. You would find that you've accounted for almost nothing, just 5%. That's all the visible universe amounts to. All that we see, all that we build, all that we are, is the cosmic minority. Dark matter outweighs that glitter 5 to 1. It surrounds us, shapes us, passes through us without a shimmer of acknowledgement. And beyond even that is something deeper, something stranger. An energy that isn't bound to mass, that doesn't pull, but pushes, stretching the fabric of space itself. Call it dark energy. It makes up nearly 70% of the universe, but that is a tale for another night. Still, there are ways to glimpse what hides. Einstein taught us, gravity bends light. And so if a massive object lies between us and a distant galaxy, the starlight detours, curving, warping, forming arcs and halos across the sky. This phenomenon gravitational lensing is, the universe revealing its own shape, a distortion drawn in light. Astronomers map these distortions. They measure the angles. They trace the arcs back to their source. And time and again, they find more mass than meets the eye. Not just more stars, but something else. Nowhere is this clearer than in the Bullet Cluster, a colossal collision between two galaxy clusters. As they crash together, their luminous gas, visible, blazing, and hot, slams into itself. It slows, it compresses, shines. But the true mass doesn't blink. The dark matter passes through untouched, invisible, intangible, indifferent. We know it's there only because the light behind it bends, distorted not by stars but by ghosts. The Bullet Cluster became a cosmic smoking gun, proof that something unseen was exerting its will, something real but hidden, a gravitational fingerprint left by something that refuses to be seen. Gravity bends light. It was Einstein who first glimpsed this strange elegance that mass curves space and space curves light. Place something massive on, invisible titan between us and a distant galaxy, and the galaxy's image will warp and stretch. It becomes a smear, an arc, a ring of light wrapped around the unseen. These distortions are no tricks of the eye. They are the fingerprints of gravity. They are the shape of what we cannot see. Astronomers trace these bends like detectives working from a shadow. They map the invisible by how it bends the visible. And in doing so, they discover mass, far more mass than the stars alone can explain. The most famous clue, the Bullet Cluster. Two immense clusters of galaxies crashing into each other. Their luminous gas blazing and hot collides in brilliant slow motion. It glows with the violence of impact, but the true mass sails silently through. Dark matter, it doesn't spark. It doesn't collide. It simply continues. We know it's there only by how it pulls on the light behind it. A gravitational echo from something that leaves no mark but its weight. A cosmic fingerprint, left by a ghost. But the Bullet Cluster is just a snapshot. To truly understand, we look to the whole canvas. In supercomputer simulations, we rewind the universe. We begin with the smallest of ripples, quantum tremors, in the newborn cosmos. Gravity amplifies them. They grow, they clump, they collapse. Dark matter gathers first, long before stars, long before atoms found each other. It forms filaments, veins of invisible mass stretching across the void. They weave together, forming nodes where the strands intersect. A foam, a scaffold, a ghostly lattice spanning billions of light years. Then slowly, ordinary matter begins to fall in. Gas collects along those filaments. It pools at the nodes. At those intersections, galaxies ignite. Stars form not at random, but where the unseen framework allows them. When we point our telescopes outward, when we map the real universe, galaxy by galaxy, we find something astonishing. It matches. The simulations, the scaffolding, the foam. The Sloan Digital Sky Survey, one of the most detailed maps of the cosmos ever made, shows the same great lattice. Like ink soaking into the watermark of the unseen. We have mapped the architecture of the universe. We have met its hidden design. We have seen the outline of the architect. And yet still we search for the builder. Still the matter that makes the galaxies dance refuses to name itself. It sculpts the stars, but never shines among them. It holds the cosmos together and leaves us only shadows to follow. Picture a particle, heftier than any atom, yet so elusive it passes through planets, people, and time itself, like moonlight through glass. This is the paradox of the Wimple, the weakly interacting massive particle, a ghost with weight, cornerstone without shape. If dark matter is made of particles, the WIMP is our leading suspect. Massive, subtle, quiet. But to catch such a whisper, we must listen in perfect stillness. Beneath the Apennine Mountains in central Italy, far from cosmic noise and radioactive interference, the XENONNT experiment lies in wait. A tank of liquid xenon, cold as the shadows on Pluto, dense, silent, ready. This noble gas, dripped of impurities and chilled to a crystalline calm, serves as the bait. A detector so pure that a single flash of light, a single photon, could be the signature of a passing WIMP, surrounding it, shielding, sensors, silence, a cathedral to absence, a chamber tuned to the rarest of interactions. Day after day, Year after year, the detectors listen, and so far, nothing. Not a murmur, not a ripple. The silence persists, but that silence is not failure, it is focus. Each null result sharpens the spear. It narrows the field. It teaches us where not to look, and where to look harder. And in that disciplined patience, there is power. Because if just once a WIMP collides with a xenon nucleus, if it releases even a flicker of energy, a glimmer in the dark, then we will have glimpsed something extraordinary. We will have touched a particle that passes through worlds and never leaves a trace. Until now. Imagine a particle, so light that a breeze could outweigh it. A trillion times lighter than an electron. It drifts through the cosmos, untouched, unbothered, born not in the hearts of stars, but in the equations of unsolved riddles. It's called the axion. It's proposed to fix a flaw in quantum chromodynamics, the deep theory of how quarks and gluons bind the heart of matter. But in solving that invisible imbalance, the axion might do something else, something greater. It might explain the darkness that holds galaxies together. In the quiet laboratories of Washington State, the ADMX experimentaxion, dark matter experiment listens. Not with telescopes, not with lenses or sensors or traps, but with a perfectly tuned cavity. A chamber of chilled silence, bathed in a magnetic field, crafted to hear the impossible. The detector is a kind of radio, but not one tuned to Earth stations. It is tuned to the frequencies of the cosmos, to the precise microwave tone an axion would hum. If it ever chose to reveal itself, an axion were to pass through the chamber, the magnetic field might coax it to convert, to become a photon, a whisper of energy, a single, pure note in the quiet. And that note to be unmistakable. So the team waits, they listen. They fine-tune superconducting sensors colder than deep space. Every day they sweep through the silence, not hoping for noise, but for music. Because if the axion exists, somewhere, even now, it may be singing. And on any night, a whisper may arrive. The sound of the dark, stepping into the light. Neutrinos. They are among the most abundant particles in the universe, and yet they pass through us like ghosts. Every second, quadrillions stream through your body, through mountains, through oceans, through the earth itself, as if none of it were there. They barely interact. Only the weak force acknowledges them. Even light doesn't notice. But nature, it seems, may be hiding something even quieter, the sterile neutrino. A hypothetical cousin to the neutrinos we know. It doesn't feel the weak force, or the electromagnetic, or the strong. Only gravity, the gentlest of whispers in the cosmic dialogue. If it exists, the sterile neutrino could be the elusive dark matter we've searched for across decades and galaxies. But how do you find what doesn't want to be found? Astronomers have turned their attention to the heavens not with nets or traps, but with eyes for light. X-ray telescopes now scan galaxy clusters, peering into their glowing cores. They are looking for a signature, not of the particle itself, but of its passing. If sterile neutrinos decay, even rarely, they may leave behind a single, silent clue, a faint spectral line in the X-ray band. A soft breath of radiation where none should be, and every so often something appears. A distant galaxy, a sliver of unexplained energy. A ripple of light that doesn't belong. Hints emerge. They fade. They reappear. Like footprints in drifting sand, visible only for a moment before the wind returns them to stillness. The evidence is not yet proof. But the universe may be leaving a trail. A thread woven through gravity, light, and silence. And those who follow it know, even the most ethereal shadows, may one day step into the glow of understanding. Not all physicists follow the path of the unseen. Some rebel. They ask a different question, not, what is dark matter? But rather, what if it doesn't exist at all? What if we're not missing mass, but misunderstanding gravity? In the 1980s, an idea emerged, bold, controversial, and elegant in its defiance. Modified Newtonian dynamics. MOND. Instead of adding invisible mass, MOND proposes a quiet revision. That at the edges of galaxies, where gravity grows weak, Newton's law of motion might need a tune. In this view, stars move faster, not because they're held by hidden matter, but because gravity itself is bending differently than we thought. And remarkably, Mond fits some of the data. It explains galaxy rotation curves without invoking the unseen. It whispers that maybe, just maybe, the laws we hold sacred are more flexible than they appear. But Mond struggles under heavier tests. When we look at galaxy clusters colliding titans with displaced mass, when we observe gravitational lensing that outpaces the visible, when we map the pristine radiation from the early universe, Mond begins to falter. The curves it explains are not the whole picture. So far, the cosmos appears to vote for dark matter, for something hidden, weighty, real. But the descent matters. In science, every idea must withstand the storm. Theories are not chosen by comfort or consensus, but by evidence, tested and retested in the light of observation. And so Mond stands not as failure, but as a reminder that the universe does not owe us simplicity, and that even in rebellion, truth can find its shape. In chilled rooms beneath steel and concrete, far from starlight and silence, the hum of modern oracles begins. Rows of GPUs, machines built for vision and speed, churn through oceans of numbers, equations of gravity, heat, and time. Here, there is no telescope, no lens to gather light. Instead, we build a universe. From scratch, we begin with a whisper, the infant cosmos just moments after birth. A fog of hydrogen, nearly uniform, but not quite. Tiny fluctuations measured in parts per 100,000 drift in the primordial soup, and then we press fast forward. Gravity takes hold. Gas collapses. Matter clumps into filaments and nodes. Galaxies blossom at the intersections. Clusters gather. Voids stretch between them like deep cosmic breaths. 13.8 billion years. In mere hours? And when the simulation ends, we look upon the result. A structure of stars, galaxies, and voids uncannily like our own. Not because we forced it to match, but because the laws of physics, when left to run, write the same story again, a lattice of light and shadow, of dark matter, gas, and time. We are not just observers of this cosmic code, we are echoes of it, built from its same logic, written in its same dust, and every time we build the universe anew and see ourselves inside it, we come closer to understanding how something so vast, so old, so silent came home, into the invisible valleys of dark matter. Hydrogen falls. Pulled by gravity, it gathers in silence, falling, heating, till it glows. Clouds collapse, pressure builds. And in the depths of these cosmic wells, light is born. Stars ignite like scattered embers. Galaxies flare to life. But these stars do not simply shine, they shape. When a massive star dies, it does so in fury, collapsing and erupting as a supernova. In a single instant, it unleashes more energy than our sun will radiate in 10 billion years. That energy sweeps through the galaxy, blowing vast bubbles in the interstellar gas, compressing some regions, scattering others. And from the hearts of galaxies, black holes stir, not just swallowing, but sculpting, firing jets of pure plasma that stretch for hundreds of thousands of light years. They heat gas, halt star formation, carve cavities in galaxy clusters. In spirals, they help trace elegant arms of dust and fire. In ellipticals, they quiet the glow, leaving vast old galaxies to drift, quenched and golden like ancient lanterns in the dark. This is not chaos. This is choreography. The push and pull of matter and void, of ignition and extinction, a symphony written in hydrogen and gravity. And all of it, the galaxies, the stars, the spaces between, play out upon a stage we cannot see, but whose shape defines us. In the great laboratories of thought and code, astronomers perform a quiet alchemy. They take the laws of physics, the data of the sky, and breathe them into silicon dreams. Simulations are run vast digital universes, born from equations and tuned by time, and then they overlay the result onto reality. Galaxy clusters, filaments stretching between them like cosmic tendons. Vast voids where almost nothing dwells. They compare the thickness of these threads, the mass of galactic cores, the size and silence of empty space, and the fit is exquisite. It's not a vague resemblance, but a harmony. A mirror, a confirmation that the story we've told, matches the universe we observe. But remove dark matter from the model, and the illusion collapses. Without its unseen weight, galaxies refuse to form. Clusters never grow. The universe comes apart before it ever begins. The light we see, stars, gas, galaxies, they are only part of the pattern. To reproduce this cosmos, you must invite the shadow to the table, the hidden mass, the silent architect, the gravitational ink in which the story of the universe is written. It is not just a placeholder, it is structure itself. And to deny it is to watch the universe fall silent before the first note is played. Dark matter didn't just influence the shape of the universe we see today, influenced when we were able to see anything at all. In the first moments after the Big Bang, the cosmos was a blinding, chaotic fog. A sea of high-energy particles and radiation, hot and uniform, stretched across an expanding space. Light could not travel freely. Atoms hadn't yet formed. The universe was not yet transparent. It was in a very literal sense, without structure and without form. In that early fog, ordinary matter, the protons, electrons, and eventually atoms that make up stars, planets, and life, was still tightly coupled with radiation. Trapped in the intense glow of the newborn cosmos, it was buffeted and scattered, unable to gather under gravity's pull. But dark matter played by different rules, carried mass but not charge, did not interact with light or radiation, and so it was free to begin collapsing under its own gravity, while the rest of the universe remained suspended in its hot plasma haze. As the minutes turned to thousands of years and thousands to millions, dark matter began to gather into clumps, then filaments, then halos, vast skeletal frameworks of invisible mass, forming in silence. These structures would become the deep gravitational wells that ordinary matter would eventually fall into. Once the universe cooled enough for atoms to form and light to finally travel freely, this early head start changed everything. Because of dark matter, gas did not have to wait to start organizing. It was drawn swiftly into the gravitational wells already carved into the fabric of space. That gas compressed, cooled, and began to collapse into stars. Within just a few 100 million years, a blink on cosmic scales, the first galaxies were born. Light pierced the darkness. The universe lit up. Without dark matter, the timeline would have been entirely different. Gas would have drifted more slowly, more diffusely. The gravitational seeds needed to trigger collapse would have been weaker, more scattered. The formation of the first stars and galaxies might have been delayed by billions of years if they ever formed at all. The night sky, as we know it, might never have emerged. What dark matter gave us wasn't just structure. It was momentum. It allowed the universe to move quickly from chaos to clarity, from silence to starlight. It was the hidden architect of the cosmic dawn, shaping not only what we see in the universe today, but how soon we were able to see anything at all. So while dark matter remains invisible to our eyes, its fingerprints are everywhere in the timing of the first stars, the birth of the first galaxies, and in the very fact that the universe did not stay dark forever. Without it, we may never have had the light to ask where we came from. The Milky Way, when observed from a distance, reveals a form so elegant, so seemingly precise, that one might mistake it for simplicity. Its great spiral arms extend outward like vast rivers of starlight, curving through space with an almost painterly grace. To the human eye, it conveys a sense of harmony, of balance maintained across billions of years. But this elegance is not fragile. It is not the result of coincidence. It is the visible expression of a hidden foundation, a structure that does not glow, that does not burn, that offers no direct sign of its presence. Surrounding the entire galaxy, extending far beyond the stars we can see, is a vast halo of dark matter, a sphere of invisible mass that outweighs all the luminous material combined by at least a factor of 10. This dark halo emits no light, no heat, it makes no sound. It passes through ordinary matter without friction, without spark, without resistance. And yet, its gravitational influence is profound. It is this unseen architecture that holds the Milky Way together. Without it, the stars would not follow their majestic paths around the galactic center. They would be flung into the depths of space, their graceful orbits shattered by the very speed at which they move. Our own star, the Sun, would be no exception. Without the stabilizing pull of the dark matter halo, the Sun, and its planets, including Earth, would have long since drifted into the void between galaxies. No solar system, no biosphere, no home. But that is not what happened. For 4.5 billion years, the Sun has remained in a steady orbit, tracing its path around the galactic core, completing one revolution roughly every 230 million years. That uninterrupted motion, that quiet constancy, has provided Earth with the time and stability needed for transformation, for oceans to form, for continents to drift, for climates to evolve and reshuffle the conditions for life, for forests to rise, fall, and rise again, for organisms to diversify, to struggle, to adapt, for intelligence to emerge. The long, slow processes that have shaped this planet from geology to biology have unfolded in a stable cosmic environment made possible, in large part by something that doesn't emit a single photon. Without dark matter, Earth might still be here, but unanchored, adrift, and likely lifeless, or it might never have formed at all. What is extraordinary is that this invisible substance has not only shaped galaxies, it has shaped the very conditions under which consciousness could appear. The ability to think, to imagine, to ask questions about the stars, only exists because those stars held their places long enough for minds to form beneath them. In that sense, dark matter isn't just part of the backdrop of the universe, it's part of the reason we're here to observe it at all. It is a silent architect of possibility, a stabilizing force that has allowed the universe not only to be structured, but to eventually become aware of itself. The calm we perceive when we look at the Milky Way is not the calm of simplicity. It is the calm of deep structure, of a hidden scaffolding that operates without fanfare, without light, but with consequences as profound as the stars themselves. It is a reminder that not everything real is visible, not everything important needs to shine. There is a quiet tension at the heart of the universe, not a clash of planets or the thunder of stars, but a slow, cosmic duel contest between two invisible forces that shape the evolution of everything we see. On one side is dark matter, the unseen mass that binds galaxies together, that pulls, that gathers, that gives structure to the great web of the cosmos. On the other is dark energy, an even more elusive entity, one that drives space itself to expand, to stretch, to accelerate outward in every direction. Together, these two forces, one that clumps and one that drives apart, govern the future of the universe. Their interplay is subtle, silent, and absolute. They are the invisible hands on the cosmic clock, ticking toward a destiny we do not yet understand. To study dark matter is to peer into the bones of the universe. To confront dark energy is to feel the breath of its lungs. And to understand how these two forces balance, interact, and eventually determine what becomes of everything is to glimpse the end game of creation itself. Let us begin with what we know. Roughly 27% of the universe is made up of dark matter, a mysterious form of mass that neither emits nor absorbs light. It doesn't glow, doesn't radiate, and cannot be seen directly. Yet its gravitational influence is unmistakable. Without it, galaxies wouldn't hold together. Galaxy clusters would disintegrate. The entire large-scale structure of the universe, the vast filaments of galaxies stretching across hundreds of millions of light-years, would simply not exist. Even more enigmatic is dark energy, which comprises a staggering 68% of the total energy content of the cosmos. Unlike dark matter, which pulls things together, dark energy appears to do the opposite. It pushes. It acts as a kind of negative pressure, accelerating the expansion of the universe, causing distant galaxies to recede faster and faster as space itself stretches. That leaves just 5%, a mere sliver, for everything else. Every star, every planet, every molecule of gas and dust, everything we've ever touched, seen, or known. All the atoms and all the stars and all the galaxies, just a footnote in the cosmic ledger. The universe, in short, is dominated by things we cannot see. And those things, particularly dark matter and dark energy, aren't just curiosities. They are the determining factors in how the universe began, how it has evolved, and where it is ultimately headed. In the beginning, there was light. Or more precisely, there was energy, hot, dense, and uniform. As the universe expanded and cooled, matter began to form. Ordinary particles emerged, atoms condensed, and light was freed to travel across space. But even then, a tension was already at play. Gravity, the pull of matter, sought to draw everything back together. Expansion, driven by the momentum of the Big Bang, and later by dark energy, pushed things apart. For much of the universe's early history, matter both dark and ordinary was dominant. It slowed the expansion, created structure, brought about galaxies, stars, and planets. But as the universe expanded, the density of matter diluted. Its influence waned. Dark energy, however, does not dilute in the same way. It seems to be a property of space itself, constant, unchanging, pervasive. As space expands, dark energy doesn't weaken, it persists. And eventually, it overtook matter as the dominant force. We are living now in that era of dark energy dominance, an era where the push of expansion is growing stronger than the pull of gravity. And that shift has profound implications for what comes next. Physicists have long pondered how the universe might end. Each possibility is a reflection of how dark matter and dark energy interact, of which is stronger, how stable they are, and whether their properties remain constant over time. 1. The big freeze. If dark energy continues to act as it does today, accelerating the expansion at a steady pace, the universe will keep expanding forever. Galaxies will drift apart, their light redshifting into oblivion. Over trillions of years, stars will burn out, black holes will evaporate, and even atoms may eventually decay. What remains is a cold, dark, and empty cosmos, a vast silence where once there was light. This is the big freeze, sometimes called heat death. It is the most widely accepted scenario. A slow fading of structure, temperature, and activity until the universe becomes, for all practical purposes, a graveyard of particles spread thin across infinite space. Next is the Big Rip. If dark energy is not constant, if it strengthens over time, then the acceleration of the universe's expansion could grow more violent. In this model, expansion becomes exponential. Galaxies recede faster and faster. Then stars within galaxies are pulled apart, and solar systems, planets, even atoms. In the final moments, space expands so quickly that it tears everything apart. The laws of physics themselves may break down. This is the Big Rip, dramatic and catastrophic ending to everything, driven by an unstable, ever-increasing dark energy. A universe undone by its own momentum. Third theory lies in the Big Crunch. In an earlier era of cosmology, when the strength of dark energy was not yet known, some theorized that gravity might eventually win. If the density of matter, especially dark matter, were high enough, its collective gravity could slow the expansion and eventually reverse it. The universe would contract, heating up, compressing, until it collapsed back into a dense, hot singularity. This is the Big Crunch, a kind of mirror image of the Big Bang, from fire to ashes, and perhaps to fire again. While this scenario is now considered unlikely based on current measurements of dark energy, it remains a possibility if the properties of dark energy change in ways we do not yet understand. The last theory is the Big Bounce. In some speculative models, the Big Crunch doesn't mark an ending, but a transition. After collapsing, the universe might rebound in a new Big Bang, expanding once more, in a cycle that repeats indefinitely. This is the Big Bounce, a universe with no true beginning or end, but an eternal rhythm of rise and fall, expansion and contraction. Here, dark matter and dark energy might participate in a deeper dance, a kind of cosmic metronome dictating the pace of creation and destruction. In all of these scenarios, dark matter plays a central role. It is the primary source of gravitational pull on large scales. Its distribution affects how galaxies form and how they move. Its density helps determine whether the universe has enough mass to eventually halt expansion. Even now, its presence acts as a brake on the acceleration driven by dark energy. And yet we still don't know what dark matter is. Is it a new kind of particle? A family of particles? Something even stranger like microscopic black holes or a relic from higher dimensional physics? If dark matter turns out to decay or to interact in unexpected ways, that would change the calculations for the fate of the universe. If it turns out to be linked in some deeper sense to dark energy, a possibility some theories entertain than understanding, it could rewrite our understanding of cosmic evolution altogether. To truly know the future of the universe, we must first uncover the nature of the matter that holds it together. If dark matter determines the structure of the universe, dark energy determines its destiny. Right now, all evidence suggests that dark energy behaves like a cosmological constant changing, a uniform woven into the fabric of space. But that may not be the full story. Some theories suggest that dark energy could evolve over time, weaken, strengthen, or even reverse. We do not yet know whether dark energy is a true constant or something more dynamic, perhaps a field, a force, or even a sign of new physics beyond the standard model. To observe it, we must look outward. We measure the brightness of distant supernova. We map the cosmic microwave background. We chart how galaxies cluster across time. Every data point is a clue. Every observation helps narrow the possibilities. And yet dark energy remains the most confounding piece of the puzzle. It is not something we can isolate in a lab. It is everywhere, affecting everything, and at the same time, completely untouchable. The future of the cosmos hinges on what dark energy is and how it behaves over time. It is tempting to imagine the universe as stable, permanent, serene, but the truth is more dynamic and more uncertain. We are not living in a finished cosmos. We are caught in the middle of an unfolding process, one shaped by invisible forces whose full nature we have only just begun to grasp. To map the future, we must understand the present. To understand the present, we must decipher the unseen. And that means coming to terms with the roles of dark matter and dark energy not as abstract ideas, but as the primary players in the greatest drama ever staged. The interplay between them, between the pull of gravity and the push of acceleration, is what will ultimately decide how the story ends. Will the universe expand into cold nothingness? Will it shatter under the weight of its own speed, collapse, only to be born anew? Or will it follow some path we have yet to imagine, governed by laws we do not yet know? To seek out the nature of dark matter and dark energy is not simply an intellectual challenge. It is an act of profound curiosity, a recognition that the most important truths may lie just beyond the reach of our senses, and that to find them, we must build new tools, ask better questions, and embrace the unknown. The fate of the cosmos is not set in stone. It is written in forces we cannot see, but that we can measure slowly, patiently, piece by piece. In learning what dark matter is, we learn how galaxies survive. In understanding dark energy, we glimpse what becomes of time and space themselves. To explore these mysteries is to look beyond the stars, not just in space, but in time. To know dark matter, to know dark energy, is to gaze not just into the heart of the universe, but into its conclusion. It is in every sense to glimpse the endgame of creation. For most of human history, our understanding of the universe has been confined to what we could see. From ancient skywatchers charting constellations to Galileo's first look through a telescope, we have followed the light. Light told us where the stars were. Light gave us the age of galaxies, the speed of expansion, the fingerprint of elements forged in cosmic furnaces. But we now know that light is not the whole story. In fact, it is only the surface, flickering skin on a much deeper invisible architecture. Beneath the shine of stars and the glow of nebulae lies a hidden world, one composed of dark matter, a substance that does not shine but shapes. It sculpts the cosmos silently, gravitationally, patiently, and so, a new chapter in astronomy has begun. A shift from observing light to tracing the invisible. This chapter demands new instruments, new methods, new imagination. And at the forefront of this effort, 3 extraordinary observatories. Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope are preparing to chart the shadows that light cannot touch. Each of these missions brings a different vision, but all share a common goal: to understand how the unseen shapes the visible, to turn the sky inside out, revealing not just where the stars are, but where gravity tells us the mass must be. This is the future of dark matter research. This is how we tighten the net, pixel by pixel. In July of 2023, a spacecraft bearing the name of one of history's great geometers launched into the quiet of space. Euclid, named for the ancient Greek father of geometry, carries with it an audacious mission: to chart the structure of the universe in exquisite detail, not just where the galaxies are, but how they are being distorted by the invisible forces around them. Euclid is not looking for dark matter directly. It is looking for its gravitational fingerprints. It finds them through an effect known as weak gravitational lensing. When light from distant galaxies travels toward Earth, it passes through a landscape shaped by invisible mass. If that mass is uneven, clumped, warped, concentrated in halos of dark matter, the light is gently bent, stretched, and distorted. Individually, these distortions are minuscule. But when gathered across millions, even billions of galaxies, a pattern begins to emerge. A map of where the dark matter must be. Euclid will survey 2 billion galaxies across more than 1/3 of the sky. It will peer back 10 billion years in time to when the first large-scale structures were taking shape. It will measure the subtle alignments of galaxy shapes, the way their images are ever so slightly sheared by the gravity of what lies between. In doing so, Euclid gives us a three-dimensional map of the universe's invisible skeleton, a direct view of the cosmic scaffolding that shaped all later formation. It also serves a dual purpose. By comparing how structures grew over time, Euclid will help us understand the expansion of the universe itself and the influence of dark energy. In this way, Euclid acts as a bridge, translator between the geometry of the cosmos and the physics that governs it. A tool not only to map where dark matter is, but to probe what it is and how it behaves on the grandest scales. High in the Chilean Andes, at the edge of the Atacama Desert, a different kind of telescope is taking shape. The Vera C. Rubin Observatory, named for the astronomer who helped reveal the existence of dark matter in the rotation curves of galaxies, is designed not to look deeper into the past, but to watch the present with unprecedented detail and frequency. Its heart is the Legacy Survey of Space and Time, a 10-year project to image the entire southern sky every few nights. Using a camera the size of a small car, capable of capturing a 3.2 gigapixel image in a single exposure, the Rubin Observatory will create a motion picture of the universe, a dynamic, evolving record of what the sky is doing night after night, year after year. Why does this matter for dark matter? Because some of the most promising clues come not just from where things are, but from how they move. By observing the tiny shifts in position of stars within our own galaxy, particularly stars on the outskirts, where the gravitational tug of dark matter becomes dominant, the Rubin Observatory can help us trace the shape of the Milky Way's dark matter halo. It will watch for subtle wobbles in the orbits of stars, signs of unseen clumps of mass. These clumps could be dark matter subhalos, remnants of the galaxy's violent formation history. Finding them is a crucial test of whether our models of dark matter structure are correct. It will also monitor the motions of dwarf galaxies and stellar streams. Long rivers of stars stripped from clusters and satellite galaxies as they spiral into the Milky Way. The gaps and kinks in these streams can reveal where dark matter has passed, like the wake behind a ship. No other instrument has the combination of field of view, sensitivity, and temporal resolution to do this at scale. The Rubin Observatory's gift is not a still image, but a moving picture, one that can capture dark matter's gravitational choreography in real time. And in doing so, it honors Vera Rubin's legacy. Not by looking for light, but by listening to what light's path tells us about what lies unseen. The third mission, set to launch later this decade, is NASA's Nancy Grace Roman Space Telescope. Sometimes called Hubble's wide-eyed cousin, Roman is designed to combine sharp imaging with a vast field of view, allowing it to capture enormous portions of the sky in fine detail. But one of Roman's most exciting dark matter tools lies in a phenomenon known as gravitational microlensing. When a massive object, say a planet, a star, or something even darker, passes directly in front of a background star, its gravity can focus and amplify the star's light for a brief moment. This is microlensing, a temporary brightening caused by the gravitational warping of space. Roman will monitor hundreds of millions of stars in the dense regions of the Milky Way, searching for these momentary events. What's extraordinary is that dark matter clumps are objects too small to form stars, but too massive to ignore, can cause microlensing events too. If they're there, Roman can detect them. This gives Roman a chance to probe a different kind of dark matter model, one in which dark matter forms compact objects like primordial black holes, potentially created in the earliest fractions of a second after the Big Bang, if such objects exist. Roman may be the best instrument humanity has to find them. But even if dark matter turns out to be diffuse and particle-like, Roman's deep imaging of galaxy clusters and cosmic structures will help refine our models. It will also serve as a powerful complement to Euclid and Rubin, offering sharp, calibrated images to anchor their broader surveys. Together, these missions form a triangulation and multi-instrument strategy to catch dark matter in the act. From motion, from distortion, from flickers of light bent by invisible hands, what's truly remarkable about this era of astronomy is that no single mission stands alone. Euclid, Rubin, and Roman are not competing visions. They're parts of a global, collaborative push to answer some of the deepest questions we've ever asked. What is the universe made of? How did it grow? Where is it going? Data from one mission feeds into another. Rubin might identify promising candidates, moving objects, gravitational anomalies that Roman can zoom in on with greater detail. Euclid's lensing maps can be compared with Rubin's time domain observations, revealing how structures evolve. Roman's microlensing catalog can provide context for unseen mass that Euclid's lensing maps suggest. This synergy is critical because dark matter is elusive, does not announce itself, it does not emit or reflect, can only be found by noticing its effect on the things that do. That requires patience, it requires breadth, and it requires instruments spread across different wavelengths, different vantage points, different philosophies of observation. In the decades ahead, we will not find dark matter through one perfect image or one single event. We will find it through patterns, through small deviations, through statistical weight piled high, like grains of sand eventually forming a mountain. This is the power of science at scale. It's not to conjure answers from nowhere, but to let the universe reveal itself, one frame at a time, as these missions come online. One already launched, another preparing its mirror for first light, a third assembling its instruments in sterile rooms. We stand on the threshold of something extraordinary. For the first time in human history, we are building telescopes not simply to look deeper into the stars, but to see the invisible. We are learning to read the distortions in starlight, the tremors in motion, the subtle flickers that speak of mass without light. We are, in essence, becoming listeners to gravity's quiet language. And through that language, we are approaching answers that have eluded us for decades. What is dark matter? Where did it come from? What else shares the universe with us? It's unseen, untouched, but essential. There is something profoundly humbling about building machines to see what we cannot. To launch cameras into space not for photographs, but for shadows. Two-point telescopes not at stars, but at the bending of their light. And yet this is the direction science must go, beyond the obvious, into the subtle. Beyond brightness, into gravity. Beyond the edge of what we know, into the silence of what sustains us. Each mission, Euclid, Rubin, Roman, is not just a technological marvel. It is a statement of belief, a belief that the universe is knowable, that its secrets are there, waiting, that even in the absence of light, truth can still be found. We do not yet know what dark matter is, but we are building the eyes to find it, the tools to trace its shape, the maps to follow where it leads. In doing so, we move closer to answering the deepest question of all. What is the universe really made of? The search continues. Pixel by pixel. Light by bent light. Shadow by patient shadow. Sometimes, what matters most is what we cannot see. Not because it hides in malice, or because it eludes understanding, but because it was never meant to be touched by light, because it was there first, before stars, before atoms, before even time had settled into its steady rhythm. Dark matter may never sparkle in a telescope lens. It may never sing in the instruments we've built to catch photons or hum in a detector the way known particles do. It does not blaze, it does not decay, it does not cry out to be found. And yet its presence is everywhere. It is the silent architect of galaxies, the gravitational scaffolding upon which all cosmic structure is hung. It gives weight to the spiral arms of our Milky Way. It shapes the orbits of stars, anchors the formation of galaxies, and sets the tempo for how the universe grows and evolves. It is the unseen thread woven through every heartbeat of matter, binding clusters of galaxies together like pearls on an invisible string. It is the hush between the stars, the background rhythm that gives rise to the symphony of everything else. And so, we search. We descend into caverns carved deep into the earth, shielding our experiments from even the faintest interference. We peer through enormous detectors chilled to near absolute zero, waiting sometimes for years. for a single glimmer of interaction, a whisper from the dark. We map the heavens with the most sensitive telescopes ever built, watching how starlight bends and stretches under the weight of invisible mass. We scan for patterns in the distortion, signs of something massive but unseen, shaping the very structure of space itself. We search in silence, in patience, in wonder. We follow the trail through archives of starlight, through supercomputers running simulations of how galaxies should form if the dark matter is there, as we believe it is. We run calculations in the small hours of the night, scribbling equations on whiteboards and in notebooks, chasing the footprints of a force that refuses to be named. And why? Because the story of the universe is incomplete without it, because the light alone is not enough, because we know, as surely as we know our own reflections in a mirror, that the cosmos holds its deepest truths, not in the brilliance of stars, but in the quiet spaces between them. Truth, in this case, may not shine, but it holds everything that does. But we keep searching, not because we are guaranteed answers, but because we know the search itself brings us closer to what matters. The night sky still holds its secrets, and if you look carefully, if you listen with patience, and think with wonder, you may feel the weight of those secrets in the motion of a galaxy, in the warping of a beam of light, in the questions that tug at your mind just before sleep. This is the nature of discovery. It begins with humility, continues with courage, and it ends, not with certainty, but with deeper questions and a fuller sense of awe. So stay curious, keep looking up, keep wondering, and join us here on Cosmic Canvas as we chase the shadows that bind the heavens together.